Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to work the question max, min, stack. What this question says is you have a stack data structure containing integers. As you push and pop items, you want to know what the max is or the minimum is at any point. So our stack starts with the number 4 in it. The max is 4 and the minimum is 4. So since there's only one value, it's both. Then we push 5 more items. Our max now becomes 42 and the minimum becomes 0. Then we pop 3 items. We lost that 0 and the 42, so now our minimum must be updated to 4 and the max is 17. Then we pop 2 more items. We get back to this original state where the min was 4 and the max was 4. Now we push 2 items. This time they're both negative. Well, 4 stays the max, but the minimum becomes negative 10. So we have this standard stack data structure. We have the standard stack methods, peek, push, and pop, which all need to function as normal. But we also want to add these 2 additional methods, getStackMax and getStackMin, that will return the max or min at any point. We also know that we can update any of these methods as needed to make these functions work. So for the brute force method, we can just search the stack and find the item that's the largest or smallest. So we go through every single item to find the max and min. We can see that the max here is 200 and the minimum is negative 5. And to find those, what we would do is pop items each time until we reach the bottom of the stack and check what the max is or min is at any point. It's going to be linear time, O of n, because we have to go through every single item. So this isn't great. The only benefit is that it's O of 1 constant space. So let's think how we can optimize on this. The first idea might be to say, okay, well, what if we just store the max and min in a variable? Then we'll know the max, we'll know the min. We won't have to iterate through each item. So let's start pushing items to our stack. We push the number 1, it becomes the max and min at this point. Now we push the number 42, 42 becomes the max, we update that value, and the minimum stays as 41. Then we push the number 3. The max stays 42, the minimum is 1. Now we start to pop items. We pop 3, there's no change, but now we pop that 42 off. Well, what do we update max to be? We don't have a history. We don't know what's happened to know what the value is before this that our max could take on. So at this point, we would actually have to iterate through the stack to find the item that is the new max. So this isn't a great solution. And we're going to incur this O of n linear time operation when we pop off a min or a max to find the new value. So how can we improve on this? Well, we can recalculate the max and min every time this value is removed from the stack, as we just saw. This is going to take that O of n linear time and constant space, but this isn't really an improvement over just searching through it. O of n time is equivalent to our brute force method. So as with most problems, the question is, can we add another data structure that has better time complexity than O of n? To do this, we would likely have to add O of n space, but we're going to make this trade-off to get faster operations by picking the right data structure. So what data structures have constant time operations? How can we beat this O of n linear time lookup? Hash tables have O of 1 constant time at the keys, arrays have constant time at the indexes or at the end, stacks have constant time operations at the end, and linked lists have constant time operations at the end. So let's walk through and understand what's happening and see which one of these makes the most sense to improve on our solution. So let's just start pushing values to a stack. We push the number 1, it's the minimum and also the maximum. Then we push 42, 42 becomes the maximum and our minimum doesn't change. Then we push the number 10. There's no change to the minimum or the maximum. We push the number negative 5. Now our minimum is updated to negative 5 from 1. We push negative 5 again. This is the same minimum, so nothing changes. Now we push the number 200. This is larger than our previous maximum, so we update the maximum to be 200. And finally, we push the number 100. This won't change our minimum or our maximum. So what does this data structure look like? Which one of the ones we discussed before could improve upon our solution? And it looks exactly like our stack. We have the stack of items that we build up that has the minimum value and maximum value. So as we push items to our stack, we can track the minimum and maximum value in another stack, 2 separate stacks for each value. So then if we want to find the maximum and the minimum at this point, we just look at the top of the stack. So we peek the minimum and peek the maximum. We know those values. Then if we were to start to pop off values, well, then we just remove the values from the stack. Pop that, our minimum is still -5, and our maximum is still 200. We pop again, our minimum is -5, but now our maximum is 42, which corresponds to what we saw earlier. We pop again, our minimum is still -5, even though we removed a -5, we still had -5 in the stack. We didn't remove the 42, so now it's still our maximum. So if we called get stack min, it would return -5, and if we called get stack max, it would return 42. We continue to pop. We lost our -5. As we saw, it's removed from our minimum stack, and now the minimum would be 1 when we check for the min by calling peek inside that get min stack method. We continue to pop, we lose the 42, and we update our minimum and maximum to 1. So now we can see we can very easily track the minimum and maximum by using 2 additional stacks. We've added this stack data structure, and we're going to get constant time operations every time we push and pop from our minimum and maximum stack. Then we can even add an additional optimization. We see that we're storing the same number multiple times every time an item's added to the stack, but we don't need these duplicates. All we need to store is if there's a new minimum or new maximum. Then when you pop items, you only pop off the min stack and the max stack if that item's removed. So when we store duplicates, we see now we have 1, which is the minimum to start, and the maximum to start. Then our new min is -5, and since it appears twice, we must add it twice in the minimum stack. So when we pop the first -5 off our original stack, we would pop this first one off the min stack. Then when we pop the other -5, we pop it off our minimum stack again. So it accounts for both -5s, and then it would be updated to 1. And then the maximum stack doesn't have duplicates, so we would just see that when we pop 200, we remove 200 from the max stack, and then the same for 42. So now we have our logic. We're taking our original stack data structure and adding 2 additional stacks inside of it that we're tracking. One of those additional stacks tracks the minimum, and the other stack tracks the maximum. Every time we push an item, we want to check if it's larger or smaller than the current min or the current max. If it's smaller than the min, then we push that to our minimum stack. If it's larger than the max, then we push that to our maximum stack. When we have duplicates, if it's equal to that top item, then we push it again to count for both occurrences in our original stack. Then, when we pop items, we check if it was equal to the top of the min stack or the max stack. If that item was corresponding to either of those, we also pop it off the minimum stack or the maximum stack. Then finally, to get the stack min or get the stack max, we simply peek that top item in the min stack and the max stack. So for our big O, we actually optimize it quite a bit. We got constant time operations. We did this by adding 2 additional stacks, which are going to be worst case O of n linear space. And now we're ready to implement our solution max min stack, which is going to take a normal stack implementation and add this additional functionality to it. We know we're going to track the minimum or maximum of a stack using additional stacks. Here, we'll just use a dynamic array as our stack implementation. So we have a max value stack, and we have a min value stack. Then to get the stack max and the stack min, all we do is peek at the top of these stacks, because as we push items to the stack, we will add an additional item if it's larger than our current max or smaller than our current min. And the current min and current max are just that top value in the stack. The real logic of this question is going to come inside implementing these push and pop methods, but the actual get stack max and get stack min will just peek at the top value of each. So let's implement those first. So when we get the stack max, we just return the last value, which is just the item at the final index. And then it's the same for the min stack. We just return the final value of our min value stack. So return the min stack at the final item. So now we actually need to track these minimum and maximum values. And the first change is going to be inside the push method. So we still continue to push the item to our normal stack, but we also need to check if it's the new maximum or minimum in either of our additional stack data structures. So first we check if our max stack has an item yet. If the length is 0, then we add the item as the max value because it will be the first item. Or we check if it's greater than the top item. And we can do this just by peeking the top item, which is calling the getMaxStack function. If it is a new maximum, we simply push this value to the stack. We need to use similar logic for the minimum stack as well. We check if the minimum item exists, and if it doesn't exist, we push it, or if it's smaller than the current minimum stack value. So we check the length to see if there are any items, or if the item is smaller than the current minimum. If it is, then we just push these values. And notice we're doing greater than or equal or less than and equal. This is because if there's duplicates, then we want to add the item again, because when you pop them off, we're going to remove an item as it's removed from the normal stack. And if it occurs more than once and is still the minimum or maximum, we need to account for all occurrences. So now when we pop, let's first store the item that is removed. So item is returned from the pop function. Now we check and see if this was also the item that is the current minimum or current maximum. So if item equals this.getStackMax, then we also pop this value off our max stack. And we do the same for the minimum. If item equals this.getStackMin. If it is the current minimum, we also pop it here as well. And then we simply return our item. And this should do it. When we push items, we check to see if it's a new maximum or minimum. If they are, then we push this value to our max or min stack. And then when we pop items, we check to see if we are popping a current maximum or minimum. If we do, then we also remove this from the max or min stack. Then when we call getStackMax or getStackMin, we simply peek at that top value, which should be the current minimum or maximum. And now we're ready to run our code. And our tests pass. So we've successfully tracked the minimum and maximum value of our stack using 2 additional stacks. We simply need to check if we also need to add a new max or min or remove the current max or min. This is a great question to understand how stacks work and a practical usage for them. Thanks everyone, and I'll see you in the next lesson.